The analysis phase of software reverse engineering. In lesson 5, I did state that the analysis phase of software reverse engineering is the stage where the source code of a software is carefully reviewed or analyzed for either of the following reasons. For the determination of a possible existence of a backdoor in the source code of the software. Another reason is to determine if there is a malicious code embedded in the source code of the software, or to determine if there are hidden functionalities of the software aside the software's officially outlined functionalities. Some of the hidden functionalities of a software may include the software stealing user data to a remote server, or if a software is converting its host device as a botnet device, or in order to crack or bypass the license requirements of the software, which by the way is illegal. Note that there are many other reasons aside these outlined purposes and reasons for the reviewing and the analyzation of a source code. But for the purpose of our illustration, I'll limit the objectives of analyzing the source code of the REFOR keylogger to these outlined objectives respectively, as displayed on the screen. In order for you to understand the encryptions in the assembly code Ghidra generated out of the executable file of the REFOR keylogger, let us go through the processes involved in the conversion of the executable file of the REFOR keylogger into its assembly code. Doing that, I will also take the opportunity to explain into details the terms and the inscriptions found in the code. On your screen now is the first conventional process involved in the reversing of an executable program into its core code, which is the machine code. On the left side of the table is the source code of an executable C program, which is to display the inscription "Hello World" onto a screen. And on the right side is the assembly code representation of the source code of the executable Hello World C program. Note that the displayed assembly code is just a small segment of the assembly code for the Hello World program. So the first conventional process is that before an executable program file is converted into its machine code, it is first converted from its source code into an assembly code. So what this means is that during the reversing process of the executable file of the REFOR keylogger, the executable file of the REFOR keylogger was first converted from its executable form to its source code, then to its assembly code. To those who may not know what an assembly code is, an assembly code is a type of a low-level programming language that is intended to communicate directly with a computer's hardware. Note that an assembly code is designed to be readable by humans, meaning you can directly decide to code or design an executable program in an assembly code. But because designing a computer program directly in an assembly code takes more time and more typing, most software engineers prefer designing their programs in a compiling programming language, such as the C programming language, in Python and other high-level programming languages, instead of coding a computer program in an assembly code. Now this is the last and also the second conventional process involved in the reversing of an executable file into its core, which is the machine code. During the second conventional process, the assembly code, which is generated out of the source code of the executable file of the Hello World C program, is converted into an assembly bytecode, that is the machine code representing the binary opcode, which is a computer-readable code in zeros and ones. So in summary, the assembly code is the intermediate programming language link between the source code of a program and the machine code. And also a source code is a human-readable programming language, while an assembly code is both a human and a computer-readable programming language, which for the sake of better and easy understanding of the instructions of an assembly code by a computer then converts an assembly code into a computer-readable programming language, which is the machine code, made up of zeros and ones. For the purpose of fast and direct interpretation of the assembly code by a computer in its machine code format, software developers often indicate with an extension such as functions, strings, .text, .data, .bss, and other memory map formats which part of the hardware components of a computer is supposed to act on a specific instructions. For instance, if a part of a program requires internet connection, for fast response and direct interpretation, a program's developer must outline the strings, the functions, or a memory map indicating the specific computer component which is supposed to process and facilitate the internet connection aspect of the program. The indication that is specifying a particular component of a computer is termed as linking. In other words, linking is the process in which references to externally defined objects like code and data are processed so as to make them operational. To simply put, linking fills in the necessary fields and informations an operating system needs to run a program. For practical understanding of linking, I have outlined the memory maps of the assembly code with a red marking at the left side of the table, which is the .text, .data, and the .bss, which are all indicating which part of a computer component is supposed to respond to a program. And on the right side of the table is the machine code version of the assembly code on the left side of the table. But for the easy and fast response of the commands of the memory map, the computer, through the conversion of the assembly code into its machine code, has denoted the commands of the memory maps in the form of a byte code, which is directly sent to the computer's corresponding component of the outlined memory maps respectively. For better and detailed explanation of the memory map of the RIFO keylogger, I will use the source code of the RIFO keylogger to illustrate its memory mapping. It is important to note that the memory mapping and the arrangement of a program tree is not universal. It actually depends on the functionality and the structure of a software. From the program tree of the RIFO keylogger, the header is the first segment of the memory map of the RIFO keylogger. Headers contains and refers to supplemental data placed at the beginning of a block of a data being stored or transmitted. To filter the source code of the RIFO keylogger for only headers, simply click on the header file in the program tree panel. Second on the RIFO keylogger memory map is the .text segment, which is also known as the code segment. The .text segment contains all executable data instructions in the memory segment, which ends up in the flash memory. To simply put, the .text segment contains all executable machine codes. In order to filter for only the .text segment in this source code, just click on the .text file in the program tree panel. The .data segment is the third memory map of the RIFO keylogger. It contains the global variables and statistic variables that are initialized, and it starts right after the .text. In order to display only the .data segment in this source code, simply click on the .data file in the program tree panel. The .bss segment, which is also known as the uninitialized data segment, starts at the end of the data segment and contains both global and statistics variables that doesn't have an explicit initialization. The .bss also ends up in the RAM. Fourth on the memory map of the RIFO keylogger is the .idata segment, which holds the import directory, that is the .edata for export. The .idata segment is used by both .exes and .dll files and links to designate the imported and exported functions. The .tls section, which is the fifth memory map of the RIFO keylogger, is used to specify the size and initial content, which is managed using memory paging and its size to quantize a page size of 4 kilobytes on an x86 machines. The seed memory mapping segment is the .r data segment. This segment is used to store constant data, and it is the read-only version of the .data segment. The last memory map segment of the RIFO keylogger software is the .rsrc segment. The .rsrc segment contains all the resources for the model. Generally, the contents of the .rsrc segment are RES files, which is produced by the resource compiler. It's important for you as a software reverse engineer to note that the main target of software reversing is to get to the assembled bytecode, which is the machine code of the software being reversed, in order to understand how the software is designed to work, its functionalities, and its representations. Meaning the source code of a software is not the main target of software reverse engineering. On the note of source code, let us learn about the differences between a source code and an object code, which in other words is referred to as a machine code. On your screen now is a diagram showing the differences between a source code and an object code. From this self-explanatory diagram, a source code is made up of both an assembly code and a high-level code such as a C programming language, Python, Visual Basic, Delphi, Perl, PHP, Ruby, C#, ECMA script, Java programming language, and etc. While an object code is made up of the bytecode and a machine code, which consists of both executable files and library files. For more detailed explanation about the differences between a source code and an object code, I have compiled all the differences that exist between a source code and an object code in a table form as displayed on the screen. Note that computers are unable to directly understand a source code, but can simply understand and execute a machine code. Let me quickly walk you through the systematic processes involved when a computer program is executed on either a 32-base architecture computer or a 64-base architecture computer. The systematic process of the execution of a computer program is made up of 4 main stages. The first stage involved in the systematic process when a computer program is executed on a computer is that the instructions of the computer that is being executed is first fetched from the memory. The second stage is the fetched instructions is then decoded into commands inside the control unit. The third systematic process is that the decoded commands is then executed and processed by the arithmetic logic unit, which is the ALU. The fourth and also the last systematic process is that the result of the operation of the issued instruction is either stored into registers or the memory. But it's important to note that this systematic process, which involves the execution of a computer program, is the same systematic process for both a 32-bit system architecture computer and a 64-bit system architecture computer. But in terms of software reverse engineering, the approach in reviewing a 32-bit system architecture-based software and a 64-bit system architecture-based software is different, though a 32-bit system architecture-based software can be installed on a 64-bit system architecture-based computer through the manipulation of the environment variable of a 64-bit system architecture computer. Since the version of my RIFO keylogger software is a 64-bit version, I will be reviewing its source code using a 64-bit approach and techniques. For this reason, I will only cover the approach and techniques used in reviewing a 64-bit system architecture software. That is, registers, instructions, stacks, addressing modes, and other features in relation to a 64-bit system architecture computer software, which I believe will not just enable and equip you to be able to review an assembly code of a 64-bit system architecture software. It will equally make you understand how the structure of a 64-bit system architecture-based software works, and as well as will enable you to identify registers, instructions, stacks, and addressing modes in an assembly code. Let's begin with the 64-bit system architecture registers. A register is a type of a computer memory used to quickly accept, store, and to transfer data and instructions that are being used intermediately by a CPU. In relation to a 64-bit system architecture assembly, it often uses either a 16-bit or a 64-bit general-purpose registers in its assembly. On your screen now is a table representing the various mnemonics of registers of a 64-bit system architecture program. As is indicated in the table, each register is represented with different mnemonics based on their size. Another observation about this table is that each register is designed to operate on different levels based on their respective representations, as is shown in the table. It's important to note that aside these registers, there are special purpose registers. One example of a special purpose register is the RIP instruction pointer, which is used to point to the next instruction to be executed in an assembly code. The RIP special purpose register has a 64-bit width. Another special purpose register is the R flags register, which is used in storing different conditional flags which is set during an arithmetical operation or sometimes used for a processor flow control. The FPRO FPR7 register is also another special purpose register used for floating point status and control registers. Last on my list of special purpose register is the RBP RSP special purpose register, which is purposely used for stack manipulation and usage. All these outline registers are all 64-bit system architecture registers. So anytime you spot any of these registers in either an assembly code or in a source code, you should be able to tell that the assembly code or the source code you are about to review is a 64-bit system architecture-based software. Let us now learn about the 64-bit system architecture instructions. To those who may not know what an instruction is a statement that is executed at runtime. In other words, an instruction is used to define the operation being performed by the CPU. Such operations may include addition, subtraction, multiplication, and etc. It's important to note that instructions can have multiple operands to define the argument for a specified operation. To those of you who may not know what an operand is a part of a computer instruction which specifies what data is to be manipulated or operated on, while at the same time is representing the data itself. Also note that a 64-bit system architecture instruction statement can be made up of 4 parts, namely the label part, which is optional, the instruction part, which is required, the operand part, which is used for specific instructions, and lastly, the comment part, which is optional. The 64-bit system architecture has a large number of available instructions, but we will focus on the commonly used ones. One of the commonly used 64-bit system architecture instruction is the move instruction, which moves data from one register to another or from a memory location to a register. On your screen now are typical examples of how the move instruction is used in an assembly code. From these examples, You will notice that the second example is different from that of the first example, with the RCX64-bit register of the second example being in a bracket. The meaning of the bracketed RCX64-bit register is that instead of moving the actual data value from the RCX64-bit register to the RAX64-bit register, the address of the data value of the RCX register should rather be moved into the RAX64-bit register. To simply put, the bracket around the RCX64-bit register is indicating that the data value of the RCX64-bit register shouldn't be moved into the RAX64-bit register. Instead, its location address should rather be pointed to the RAX64-bit register. It's important to note that both the RAX and RCX64-bit registers are all examples of general-purpose registers. The addition and the subtraction instructions is another set of common instructions. The function of the addition instruction is to add two values together, but stores the result of the added values inside the first argument, which is the first value. This is a typical example of how the addition instruction is used in an assembly code. This code is set to add both the value of the RAX register to the value of the BRX register, but its outcome will be stored in the RAX register, meaning at the end of the execution of this code, the value of the ARX register will be made up of the original value of the ARX register plus the value of the BRX register plus the outcome of the addition of both the value of the RAX register and the value of the BRX register. In relation to the subtraction instruction, the value of the second operand is subtracted from the first operand, and the result is also stored in the first operand, just as that of the addition instruction. So always bear it in mind that both the addition and the subtraction instruction all stores its final results in the first operand or the first register. Third on our list of common set of instruction is the AN instruction and the XOR instruction. The operations of both the AND instruction and the XOR instruction are common with digital logic, so those of you who are familiar with digital logic may know about these operations. And just as the addition instruction, the subtraction instruction, and the move instruction, the AND instruction and the XOR instruction also stores its results in the first operand when used to perform binary operations on two operands. The XOR instruction can be used to reverse selected bits in an operand while preserving the remaining bits of the operand. The fourth on our list of common set of instructions is the jump instruction and the call instruction. The jump instruction is used to change the code being executed and also used to modify the value in a EIP or RIP instruction pointer. To simply put, the jump instruction causes a section of an assembly code to jump to another pointer location in the code. While the call function is used to implement function calls in order to fix up and push a RBP and a RIP instructions onto a stack appropriately before it is jumped to a new location. The difference between the jump and the call instruction is that in the case of the call instruction, when a call instruction is done calling a function, it actually knows the location to jump back to. On my list of common set of instruction is the compare instruction, which is denoted as CMP. The compare instruction is used to perform a compare operation by subtracting the operand that is provided, but except that there is no storage space with the compare instruction. For this reason, the result of the compare instruction is never stored. But if in case there should be an overflow in relation to the result of the subtraction operation of the compare instruction, the flag fields in the R flags register will be set. Note that bits found in flag registers are very important because the jump instructions has different variants that check those flags before performing the jump instructions. This is an example of how the compare instruction is used in an assembly code. What this code of compare instruction means is that the RAX register contains 0, and if we subtract 3 from the 0, the jump 0 instruction will then return. But if the flag is not set, the jump 0 instruction wouldn't return, meaning it wouldn't modify the EIP. Let's now talk about the 64-bit system architecture stack. A stack is defined as a data structure containing elements such as functions and other various operations in a contiguous memory. For the purpose of our illustration, I will only talk about two specific instructions that interact with stack. That is the pop instruction that reads from the stack and the push instruction which writes to the stack. In relation to the push instruction grows the stack by 8 and stores the operand content on the stack. This is a typical example of how the push instruction is used in an assembly code in order to grow the stack by 8 for the storage of the operand content on the stack. On your screen now is a typical example of how the pop instruction is used in an assembly code. In the case of the pop instruction loads the value pointed by the RSP register into the operand, meaning the pop instruction does the exact opposite of the push instruction. For better understanding of how the stack works, this is an animation demonstration of how the pop instruction and the push instruction works. To the left is the sequence of instructions, that is the push RAX, push RBX, and the push RCX. In this demonstration, all the sequence of instructions which has been outlined on the screen will all be pushed under the stack, and then we'll pop the value from the stack into the RAX register. So upon initiating the first instruction, the RAX register is pushed under the stack. And upon the second instruction execution, the RBX register is equally pushed under the stack. Upon the execution of the third instruction, the RCX is then pushed onto the stack. But upon the last instruction, which is the pop RAX instruction, the program then pops whatever value is on top of the stack and then stores it on the RAX register. So at the end of the execution of all the instructions, this is the final result of the stack. Note that the stack is important for understanding how functions are called later and often used to store local variables. The addressing mode of a 64-bit system architecture software is the last 64-bit system architecture feature we'll be covering. One may ask, what is an addressing mode? An addressing mode is used to specify how to calculate the effective memory address of an operand by using the information held in the register's contents contained within the machine instruction. Meaning an addressing mode instruction can access registers and memory in various modes. This is a practical example of how an addressing mode is used in an assembly code. What this code is instructing to do is to add the value of the RAX register to 14, and then is to store the result in the RAX register. You can also perform an addressing mode instruction on a register-to-register basis like this example. With this particular example, the value of the RAX register is cleared. An addressing mode instruction can also be used in an indirect access instruction like this example, which is instructing the addition of the value pointed to by the RBX into the RAX register. Another example of how an addressing mode instruction can be used is this. This addressing mode instruction code is instructing a move of the address 8* RAX plus RCX plus 12345 into the RBX register. It is important to note that anytime you see a value in a bracket in an addressing mode instruction code, it is indicating that the value in the bracket is a pointer, meaning the value in the bracket is a reference of an address location. I have animated this instruction exercise, which consists of all the instructions we've covered so far in this lesson. The first instruction is to move the 2FFF into the RAX register, and upon the execution, this is the result. The second instruction is to move the value into the RBX register, and upon executing, this is the result. The third instruction is to add the two values, which is the value of the RAX register and the value in the RBX register, into the RAX register. Take note of the results table. You'll notice that as I execute the third instruction, the value in the ARX register will increase from 2FFF to 3FFF. The fourth instruction is to move 10,000 into the RCX register. And this is the outcome as I executed this instruction. The fifth instruction is to subtract the value of RAX register from the value of the RCX register. But its result will be stored in the RCX register, since the RCX register is the first operand. And as I execute the fifth instruction on my computer, you will notice that the results of the RCX register will change from 10,000 to C001 on the results table. The sixth instruction is to add the value of RCX register to the value of the RBX register. And since the RCX register is the first operand, the result of the addition of the value of the RCX register and the value of the RBX register will be stored in the RCX register. The seventh instruction, which is a compare instruction, is to compare the value in the RAX register with that of the RBX register. And from the results table, the value in the RAX register is greater than that of the RBX register. The result of the execution of the seventh instruction is based on the condition of the eighth instruction, which is a jump instruction requesting a jump only if the greater than flag has been set. And since the value in the RAX register is greater than the value in the RBX register, the command will jump to the last instruction, which is the move RAX 0x1, and then the command will return to begin the process again. I hope with this example you now have a better understanding of how the instruction operates in a code. We had to go through the basis of how the registers, instructions, stacks, and the addressing modes of a 64-bit system architecture software works, in order for you to have a better understanding of the underlying assembly code, though Ghidra has a decompiler. Let's begin the analyzation phase of the reversing of the refor keylogger by first reviewing the source code of the refor keylogger for the purpose of identifying if there is any possible existence of a backdoor as our first objective of the analyzation phase. Before we begin with the practical session, which is the reviewing of the source code of the refor keylogger, let us first learn about backdoors in order to have a better understanding about backdoors, how it works, its types, and how to easily identify them. A backdoor is a type of malware that negates normal authentication procedures in order to access a cyber system, which could be a software, a hardware device, or a network. but often in the context of hardware devices and networking infrastructure, backdoors are mostly in the form of a software. To simply put, a backdoor is a malware or a malicious script which secretly allows access into a cyber system. So this is how a backdoor of a system works. It works by granting its creator or a cyber adversary the remote access to a system network or the resources within an application, such as databases and file servers, the ability to remotely issue system commands, and sometimes to even update the malware or the backdoor itself. Types of backdoors. There are two main types of backdoors, but of many forms. The two main types of backdoors are the conventional backdoors, which are often hidden parameters or redundant interfaces which requires human authentication or authorization for its activation. Most conventional backdoors are often protected by password authentications, which has an administrative interface. That actually makes conventional backdoors vulnerable to brute force attacks, dictionary attacks, and lockout attacks, depending on the system architecture. So anytime you come across a conventional backdoor, just exploit it with either a password brute force attack, a password dictionary attack, or a lockout attack. Note that a conventional backdoor can easily be detected by a knowledgeable, skillful, and a smart cybersecurity researcher. The second type of backdoor is the unconventional backdoor. Unconventional backdoors are types of backdoors that require the authentication and the authorization between system applications and hardware components for its activation, making unconventional backdoors very difficult to detect, difficult to fix, and sometimes almost impossible to even fix. I consider unconventional backdoors as the most dangerous backdoors and also a zero-day exploit, which can be exploited by any cyber adversary for a very long time. Now that we know the various types of backdoors, let us now identify the various forms of backdoors. Forms of backdoors. There are three main forms of backdoors. First on the list of forms of backdoors is crypto backdoor. Crypto backdoors are backdoors designed as a weaknesses for a particular key message or prompt. The second form of backdoor is system backdoors. A system backdoor is a malware design backdoor designed to compromise a system infrastructure. This particular form of backdoor often relies on social engineering attacks for its initial execution. The last and the third form of backdoor on our list is application backdoor. Application backdoors are modified legitimate programs designed to bypass security mechanisms. Application backdoors are often inserted by those who have legitimate access to a source code or the distribution binaries of a legitimate program, which is already in use or running on a system. So anytime you happen to discover an application backdoor in an application, doing a software reverse engineering, look no further in search of its source, since it can only be inserted by an IT staffer or mostly the developer of the said application. Since an IT staffer and an application developer both have easy access and legitimate access to both the source code of the application and the distribution binaries of the application. But also bear in mind that hackers can equally plant an application backdoor into an application. That is only if a hacker has access to both the source code and the distribution binaries of the application. Application backdoors are actually very difficult to identify within a system, since it's a legitimate application known by a system, and they can easily result in system compromise as well. To those of you who prefer downloading paid applications and media files from torrent sites, I advise you to stop, because almost all the applications and media files which are uploaded onto torrent sites all have application backdoors embedded on them. Let us take a quick look at targets of application backdoors. On the screen now are targets of application backdoors. First on the list is web applications, followed by server applications, then network appliances, and operating systems. Based on the detailed explanation of system backdoors, its types, its target, and how it's designed to work, I believe we can now proceed to review the source code of the REFOD keylogger for the purpose of identifying any possible backdoor embedded into its source code. To those who are new to software reverse engineering and the reviewing of source code and binaries of programming, I'll try as much as possible to explain into details all the relevant programming inscriptions in the RIFO keylogger source code during the reviewing process. But I wouldn't be able to review this source code on line basis since this source code has over 5,000 lines, which will take us about approximately 2 to 3 days to complete the reviewing of this source code. But I believe with the detailed explanation of all the relevant programming inscriptions of this source code, you'll be well equipped to review this source code all by yourself. Before analyzing the assembly code of the RIFO keylogger, let me first explain the various column arrangements in this assembly code. The first column, which is made up of all digits, is known as the address field. It represents the memory address where a particular data is located. This second column, as I have indicated, is the raw byte column. This is representing the machine code instructions of the memory address. The third column is the mnemonic field. This represents the instructions that has been disassembled from the opcode. The fourth is the operands, which is representing either the register or the memory location used by the instruction. This is the XREFs, and it stands for cross-reference. This column is indicating that other locations of instructions has been referenced to an address. In order to navigate between two marked cross-references, just double-click on any of them. One unique and great feature about Ghidra is its ability to decompile an assembly code. This comes in handy for those who are unable to read and understand an assembly code. In order to convert an assembly instruction to a C code, just highlight the section of the assembly instruction that you would like to convert into the C language, and then click on the Decompiler tab. Before Ghidra converts an assembly instruction to a C code, it first uses its P code to abstract the assembly instruction into a P code operations. To those who are wondering what a P code is an intermediate language which is shared across all processors. This is possible because all processors are created and programmed with a SLA language. For more detailed scrutiny of an assembly instruction, you can decide to use the byte view by just selecting the section of the assembly instruction you want to scrutinize, and then proceed to click on the byte view tab. For the easy identification and the filtering of the various functions and strings in an assembly code, you can use the Define Strings tab. From 15 years experience in reviewing source code, I know some common strings that most software engineers often use to hide their backdoor. So from my experience, I want us to search for some particular strings. And if we don't see any of those strings, then we'll have to spend more time to review the source code line by line in search of a backdoor to see if the RIFO keylogger software has a backdoor. Since my version of the RIFO keylogger software is a Windows-based software, let me first search for the common control library string, which is actually a Windows processing file. Well, it seems the RIFO keylogger source code has a common control library string. Disclaimer: this doesn't mean that the RIFO keylogger software has a backdoor. It's just that this particular string is often used by software developers to hide backdoors. This is because the comctl32.dll file provides common Windows objects such as list boxes and combo boxes to Windows programs written in the Visual Basic language, and also the fact that it pertains to computer network security, which when deleted or removed, it will result in the non-functioning of the Windows operating system itself and other Windows programs written in Visual Basic. For this reason, most anti-malware and antivirus softwares either skip or refuse to scan the comctl32.dll string file during malware scanning. Note that Windows strings which are found in source codes are often designed to just make changes in the original Windows default strings, but a more sophisticated strings can be designed to replace the default Windows string file. But in this case, such strings, in addition to a malicious script, also have the same data as the string it will be replacing. In relation to the interpretation of the comcontrol32.dll string as assembly instruction session, the 00419D70 is the memory address location of the common control library data, while the second field, which is the raw byte data, is representing the machine code instructions of the memory address of the comctl32.dll string. In order to see the full raw bytecode, just highlight on the session and then click on the Define Bytecode button. If in case you would like to affirm if the raw bytecode is indeed representing the COM-control32.dll string, just copy the raw bytecode into any hexadecimal converter. Back to the source code of the refor keylogger. The third field, which is the mnemonic field, is represented with the data segment register. The function of the DS register is to store the starting address of the Common Control Library data segment. On this note, I highly recommend you to always research about identified strings and registers in the source code in order to determine why it's being used and to know more about its functionalities. That is if in case you have no knowledge about it. As I said earlier, because the refor keylogger is a well-known and a patronized keylogger software, I'm limited to perform more detailed analysis on its source code, but I'll be spending more time to do so during my software reverse engineering bootcamp. But I believe with the detailed explanations of the methodologies and the procedures involved in software reverse engineering, I have equipped you enough to perform a detailed analysis on strings, registers, and instructions of a source code. Now let's move on to the third objective of reviewing this source code. That is for the identification of any possible malicious script. As I scroll through the source code, you'll notice that some of the source code inscriptions are red color coded. By default, Ghidra flags all encrypted, suspicious or malicious scripts in a red colored coded inscription. So anytime you are performing a reverse engineering with Ghidra and you come across red color coded inscription in the source code, know that Ghidra in its own patterns and during the analyzation of the source code, either identify that particular assembly instruction as encrypted, suspicious or malicious. It doesn't mean that if there is no red color inscription in a source code, that source code has no malicious script. More sophisticated malicious scripts are not easy to be detected for flagging. For this reason, I advise you to always analyze every source code line. Let us now randomly pick any of the red color coded inscription section to analyze it in order to determine if it has been flagged and red color coded for the purpose of it being either an encrypted session, it being a malicious script, or just a suspicious script. Before we begin to analyze this flagged assembly code, let me show you a trick to simply determine if a section of an assembly code has been flagged for the purpose of it being encrypted. The trick to determine if a section of an assembly code is flagged as a result of it being encrypted is to simply place the cursor of the mouse on the red color code inscription, and if there is a pop-up note like this, containing either an embedded or an encrypted data, then the section of the assembly code was flagged as a result of it being encrypted. To those of you who can code in and interpret an assembly code, you can choose to go ahead with the interpretation of this session. But for the sake of those who are unable to code and interpret an assembly code, you can choose to convert this assembly code to either a C code or a machine code. But for the purpose of this illustration, let's convert this assembly code into a C programming language in order to have a better understanding and an alternative interpretation of this particular assembly code instruction. Just at the look of these two different interpretations, you can easily deduce that both interpretations are way different from each other, but that of the C programming language is more simpler than that of the assembly code. In relation to the interpretation of the highlighted assembly code instruction in C programming language, the second line in the C code is just a warning comment, while the fourth line of the C code is a conditional call instruction demanding a return of the rule of a Boolean variable, that is, if a statement is either true or false. The enum calendar info XW function in the fifth line is used to receive a calendar identifier in addition to the calendar's information from the parameters listed within the bracket. It is important to note that any application that is designed to be executed on only Windows Vista and later versions of Windows operating systems is using the enum calendar info xx function in preference to the enum calendar info function. The first parameter in the bracket, that is the call info underscore enum pro cw ip call info enum proc parameter, is pointing to an application which is a defined callback function, while the lcid parameter is representing the source language in which the calendar information should be displayed in, that is, if it should be displayed in English or any other language. The next parameter is the calendar identifier. The calendar identifier is specifying the type of calendar information to be requested. That is, if the calendar information should be made up of the day, the month, the year, or the time of an event. While the call type parameter is specifying the type of calendar information to be called. The instructions beginning from the 7th line to the 14th line is requesting that if the boolean bvar1 variable is equal to the value in the enum calendar info w syntax, then the program should return bvar1. In summary, this section of the assembly code is to simply fetch specific date and calendar information. This kernel32.dll function here is a function used to call the enum calendar info x function. So based on our findings and the interpretation of this section of the assembly code, both the kernel32.dll function and the enum calendar info x function are all red colored coded by Ghidra because they both have hidden instructions concealed in them and not because they are malicious or encrypted. I believe that with this detailed guideline and simplified explanation on how to analyze the red color code instruction, you can easily analyze the rest of the red flag assembly instructions. But if in case you get stuck with any of the functions, just research or Google about that particular function in order to know how it works and its related syntax. In relation to the side effects and the vulnerabilities of the Refor keylogger software based on its source code, I am limited to give much details about it, since the Refor keylogger software is a commercial software, so I wouldn't want to face any lawsuit or discourage its users from downloading or purchasing it. But note that any listed Windows default registry keys and files that has been outlined in the Refor keylogger source code has a high tendency of it being vulnerable, which in the documentation phase I will disclose in the reviewing summary report of the Refor keylogger software. Let's now review the Refor keylogger source code in order to identify the software's license requirement assembly session. At the beginning of this lesson, I stated that I will only point out the part of the assembly instruction session which is instructing a user to either license or register the Refor keylogger software. And in addition, we'll only talk about how to crack and bypass the license requirements of this software. But for more detailed explanation and technical know-how on how to bypass or crack any software license requirement, I encourage you to join my Master Source Code Reviewing and Software Reverse Engineering Bootcamp course. Before I point out the parts of the section of the assembly instruction which demands a user to either license or register the Refor keylogger software, let's first learn about the various types of software licenses. In general, there are 5 main types of common software licensing models. 4 out of the 5 main types are examples of open source licenses, which allows a user to reuse the code for a period of time, while the other type of software licensing model prevents a user from reusing a software registration code or a software license key. One of the 4 open source license models is the public domain license model. The public domain license model is the most permissive type of software license model. When a software is in the public domain, anyone can modify it and use the software without any restriction. But as a software reverse engineer, I advise you to always analyze the software in order to make sure that it is secured before adding it to your own code base. It is important to note that A software code that doesn't have an explicit license is not automatically in the public domain. This includes software code snippets you find on the internet. The permissive software license is one of the 4 open source license models. The permissive software license is also known as the Apache style or the BSD style. This particular type of open source license model contains minimal requirements about how a software can be modified or redistributed, and perhaps is the most popular software license model used with free and open source software. Aside the Apache license and the BSD license, another common variant of the permissive software license is the MIT license. The Laser General Public License is another type of software license which allows you to link an open source libraries in the software. If you simply compile or link a Laser General Public License library with your own code, you can release your software application under any license that you want, even as a proprietary license. But if you modify the library or copy part of it into your own code, you would have to release your application under similar terms as the Laser General Public License. The 4th open source license model is the copyleft license, which is also known as the reciprocal license or the restrictive license. The most well-known examples of a copyleft or a reciprocal license is the General Public License and the Creative Commons Share Alike licenses. These licenses allows you to modify the license code and distribute new works based on it, as long as you distribute any new works or adaptations under the same software license. For example, a component license may be free to use and to be distributed for personal use only, but any derivative that you may create with a component license will also be limited to personal use only. The catch here is that the users of your software would also have the right to modify the code. Therefore, you would have to make your own source code available. But of course, exposing your source code may not be in your best interest. The last type of software license model, which also happens to be the only non-open source software license, is the proprietary software license. The proprietary software license is the most restrictive software license. The idea behind the proprietary software license is that all software rights are reserved, and as a result, such softwares may not be modified or redistributed by a third party. Now that we have learned about the various types of software license models, I advise you to always make sure that a software you seek to crack or bypass its licensing requirements is an open source software and not a software with a proprietary software license, since the owner of a proprietary software license can sue you in the law court for modification or for the redistribution of his or her software without his approval.
Purchase your tracks today. Bite your chest. Kill this beat for me. Bite your chest. Kill this beat for me. Batsy beats. Purchase your tracks today. Write your chest. Careless wait for me. Sweaty beat. Sweaty beat.